All right. Welcome to this mini class on modeling organizational learning. I'm very grateful for your interest and enthusiasm for the topic. So what I'm going to try to do in 4 sessions is to not just cover some of the core ideas in the literature on organizational learning, but also try to give you some tools to think about organizational learning in a more systematic and formal way. And in particular, we're going to use the toolkit of multi-agent reinforcement learning to formalize a lot of the arguments we sometimes make verbally, and not just for the purpose of formalizing stuff, but also by doing so, sometimes we discover surprising things, right? That's really the big payoff to formalization, as you know. This picture that you see on the first slide here is from Linda Argotti's book on organizational learning, which if you haven't read, I strongly recommend that you get hold of a copy and read it. I might even have a soft copy that I'm happy to share with you. But it's a really nice overview of the field written, I think, around 2012 or 2013. So it's been a decade now, but still, I think, is one of the best single point references, if you like, on the literature on organizational learning. What would be interesting also is to see the roots of this field, because that's covered very well in her book. And this picture is really where a lot of the action begins. This is a picture of a learning curve. Okay, so what you're seeing here is a reduction in something, usually a cost, through cumulative output. So people get better by doing stuff. And that really, in a nutshell, is learning by doing. Okay, this is how it's been conceptualized for a long time. So this is Linda's very influential paper in Science, along with D. Apple, in which they showed and documented these kind of learning curves. So in terms of motivation for this course, the reason I think this is important is that organizational learning is often used to explain a range of organizational behaviors. Okay, whether it's M&A, whether it's alliances, whether it's joint ventures, it's actually stuff on the shop floor, like in Linda's work, even the design of contracts and the design of incentive systems. So a lot of these phenomena, which look superficially very different from each other, can often be explained by thinking about them as a process of organizational learning, where the organization gets better usually at doing something over time, or at least does it differently over time, right? The better is not guaranteed, which is one of the important points we'll come back to later. But some change over time is often implicit in these accounts. Now, what I want to also use this 4 sessions to do is to try and bring together not just this literature, which originates in the learning curve world, but also 2 other literatures which have developed somewhat in parallel, okay, but actually are very closely tied to the concept of organizational learning. One is the stream of work on organizational adaptation. Now, organizational adaptation is not a new topic, and the seeds of that were, of course, in the Carnegie School's work by March and Simon and others. But, and of course, then Thompson, and then Lawrence and Losch, and all the classics that you've probably read at some point. But the formalization of organizational adaptation, in some sense, begins with Leventhal 97. And the use of the NK framework to think about organizational adaptation versus selection, right? This is a paper that all of you read in the first year research methods class. So you might remember some of the core ideas there. And in that literature, the focus is not on learning curves, okay? It's often more on fitness over time. And at one level, these are just mirror images of each other. So a reducing cost over time function, if you flip it around, becomes an increasing performance over time function. Okay, they're really the same thing. But more importantly, I think that literature on adaptation focuses a lot not just on the improvements over time, but in the fact that organizational adaptation can get you stuck. Okay, so you can accomplish stability, but not necessarily high performance because of the pathologies of local search. That's been like a very salient idea in the organizational adaptation literature. A third literature has to do with performance feedback. Right, and some of the major contributors to this are here at INSEAD. So Henry Graves' work, for instance, also deriving from the Carnegie tradition, but took a different direction, essentially deriving from Sayat and March, which looks at the question of organizational performance over time as a function of prior performance, and how organizations respond to that, in particular, by increasing the degree to which they search or explore when the performance falls below or lies above some aspirational level. Okay. So these 3 ideas, the learning curve literature, the adaptation on rugged landscapes literature, the performance feedback literature, broadly, they're all about org learning. But how do they connect to each other? How are they related to each other? That's partly what I'm going to try and emphasize in this course, that they are in fact very intimately connected. And the framework we're going to use can be helpful in understanding all three of them, finding points of connection, points of contradiction, and obviously opportunities for future research. Okay, so this is very much the theoretical agenda, if you like, of this course. The other second point on the theoretical agenda is that all these three literatures, whether it's the org learning literature or the adaptation literature or the performance feedback literature, have by and large tended to take a view of the organization as a unitary actor. So it's a single entity, right? And we could essentially assume the behavior of the firm is like the behavior of this single entity. And in many ways, the analogy to individual search or learning is one-to-one. Often the same sorts of equations, the same sort of arguments are being made. And we don't really distinguish much between whether what we're looking at is individual learning or it's organizational learning, individual adaptation, organizational adaptation, individuals learning from performance feedback or not. Increasingly, I think the current generation of work in organizational learning is beginning to pay a lot more attention to the point that there are qualitative differences between organizational and individual learning. Okay, we will get into this in a lot more detail, but at this point, I want to summarize it by saying there are really two basic differences between organizational learning and individual learning. The first is context. So individuals, when they learn in an organizational context, may learn differently than when they learn outside of an organizational context. So individual learning itself changes, whether it takes place in an organizational context or not. So think about you taking this course on your own, just watching some videos, versus taking it in a class with some group assignments and discussion and exercises. So it's still individual learning, but they qualitatively will look quite different in the two cases. So context is one reason why they're different. The second is aggregation. Independent of the effect of context, when you put the learning of different individual actors together, the aggregate effect is not just a linear sum, right? So a sum is also an aggregation, but what we're saying here is it's typically not a simple aggregation based on a sum. And the reason it's not simple is because within organizations, you have interactions. And as we'll see, the interactions come in two flavors. Either they are interdependence, so the returns to my action depend on what others are doing, or it's influence. So I can change the way you think based on what I say. And these can go together or they can go separately. But interactions are going to change the aggregation process away from a simple addition to something more complicated. And context will change the very behavior of actors just because we put them in an organization versus let them stay outside. So context and aggregation together really make quite a significant difference between individual and organizational learning. And this is a point that now more and more people appreciate and are working a lot actively in this domain. And what this course is really trying to do as a second big agenda item is to give you a set of modeling tools that can help us think carefully about organizational learning in a way that recognizes aggregation. Okay, the contextual effect, the effect of how individuals change their behavior when they are in an organization versus not, is something that modeling typically can only help with but cannot answer. The reason is it's an empirical question, right? So do people behave differently when they are in a context versus they are on their own? The models can help us think about the problem, but ultimately it's a data problem. We have to go out there and collect the data and understand what's the difference between individuals working on their own versus individuals working in a group. But the models can be very helpful in showing us what to look for. That's the context part. On the aggregation side, it's actually the opposite. There is no way you can progress without a model. Okay, the models are particularly helpful when thinking about aggregation because aggregation, as I said, is typically not a simple linear sum. It's not a simple addition, right? It's more than that. And that means it gets very quickly quite complicated. So both the interactions in a period of time as well as across time can become very complicated. And as you recall, that's the classic reason why we use formalization, right? We use formal models when interactions become complicated, either within a period of time or across time or both. And org learning is exactly about that sort of complication. Okay, so that's kind of the high level objective for what I'm trying to do here with these series of lectures. Now, before I progress further, it might be helpful to get a quick sense of how many of you are actually working on topics that relate to org learning. So if you could just do a show of hands, maybe by raising your hands. You can use the raise hand function inside Zoom. It'll give me a sense of how many of you are doing research or plan to do research, which is around organizational learning. Okay, so I'm seeing only a few hands here at this point. 1, 2, 3, 4. Okay, good. So let's see if this number changes. 6. Let's see if this number changes by the time this course is over. Okay, and I'm okay for it to change in either direction. It may be that at the end of this, you realize this is clearly not what you want to do. That's fine too. It may be also we have like a stochastic equilibrium where some drop out and some drop in, and we're still at 6. That's okay too. All right, but yeah, good. So that gives me a sense of the broad interest here. So partly I'm going to try to convince you that even if you're not directly looking at something that now looks like org learning, by the time we are done, you'll recognize that thinking about your problem using an org learning lens can often generate very interesting new hypotheses. You may choose to pursue them, you may not, that's your call, right? But it will give you some new ways of thinking about classic problems that you're already familiar with. Okay, so the agenda today is the following. As I said, because we are working at the intersection of 3 different literatures, the literature coming from the learning curve tradition, the literature on organizational adaptation from the NK landscape world, the literature on performance feedback, and to which I would add a 4th, which is really the most, I think, technically sophisticated literature, but it's not in our field, it's in computer science, which is multi-agent reinforcement learning. So when you work at these intersection of multiple fields and you're trying to integrate, it's really important to get the terminology right. Okay, otherwise we could be talking about the same things in very different ways and not making much progress. So a good chunk of today's session is really to make sure that we have common understanding of certain concepts, which we will then use again and again over the next 4 sessions. Okay, some of this hopefully should not be new because I did assign pre-readings and some pre-work. So I'm hoping you've all done the pre-readings and you've also done some of the pre-work. So you're a bit familiar now with how to set up a simple single agent model of adaptive reinforcement learning. You've replicated the exercises from the TOM website and you're kind of broadly familiar. What I'm going to touch on today, in addition to that, is to give you a bit more theoretical depth and foundations on ideas like what exactly is adaptive rationality? How is it different from other forms of rationality? Okay, what's the alternative to learning by doing? Is that the only way that learning happens, or are there other ways in which learning can happen? What's a Markov decision process? Why is it connected to anything we're doing? It's useful to know these things. And finally, how do computer scientists think about reinforcement learning and learning in general? And what can we learn from what they do and what can we not? And why not? Right? These are all important things for us to know if you're going to make progress on how we will think about organizational learning. We'll then move on to looking in depth at the model that you've already gained some familiarity with, but I'm going to kind of debrief and walk it through step by step. And we will also review the results of the replication exercise of the single agent model of adaptive reinforcement learning. Okay, that will give us, I think, very solid foundations for doing what the rest of the course is supposed to do. Any questions at this point on either content or ideas or topics, what we're going to cover? You okay? All right. All right, let's begin with some very basic concepts. So what's the word organization mean when we're talking about organizational learning? So hopefully by now you've seen this content, so this should not be new for you, right? So we're really thinking about organization in a very, very broad way. It's any multi-agent system with identifiable boundaries and has some kind of a system level goal, and the constituent agent's efforts are making a contribution towards the goal. Okay, that's it. So by this definition, we can include a team, a department, a group, a company, an ecosystem, a platform, if you like, or even if you like, in the limit, an entire country as an organization. We don't really distinguish based on size. What matters is it's a multi-agent system. It has some boundaries because we want to study the system as opposed to its context. That doesn't mean that the boundaries are stable. So membership can be changing over time. That's perfectly fine. In fact, some of the classic models of organizational learning are about changes to membership and the effect of that on the organization's performance and culture. So think about March 1991, right? So it does not require that the membership is stable, but it does require you to be able to say at any point in time who's in and who's out. Okay, that's all it means to say there's a boundary. There must be a system level goal, which could be performance in many contexts, or it could be something quite different, right? Nothing that we talk about here restricts these ideas to only looking at firms. These could be NGOs, these could be government entities, these could be nonprofits of various kinds. And in fact, it could even be systems where no member of the organization is even aware of what the goal is. Okay, so these could be implicit organizations. So think about communities of practice. So in a community of practice, a group of people are working together without possibly even knowing they're working together, because their interactions are second order and third order. And the community as a whole is accomplishing something, but it doesn't mean that any individual in the community knows about this. Maybe they do, maybe they don't. It's not necessary for them to know. Okay. And finally, of course, we are crucially interested in understanding how the efforts of the individuals somehow aggregate up to creating the organization level goal. So that's the very general view we take of organizations. Okay, so when we talk about org learning, we could be talking about the learning of a team, a department, a group, a company, an ecosystem, whatever you want. It could even be just a dyad, right? A set of two people with some kind of a common objective, which they may not even be explicitly aware of, can be treated as an organization. So another way to make this point really is to say, we're not into the legalistic definition of what is or is not an organization, right? That's not particularly interesting. The more interesting question is, if you look at any system which has multiple actors and that system seems to have an objective, could we understand how it works by treating it as an organization? So I call this the organizational stance. So to look at any multi-agent system and ask, what can we learn if you were to think of this system as an organization? So a mob or a crowd could also be treated in this way as an organization, as long as we are clear what we're trying to do, right? We're not trying to establish some legal precedent of saying this is an organization, this is not. What we're trying to understand is, can we gain some insight into how the system works by thinking about it as a multi-agent goal-oriented system? So to put it very simply, any group with a goal is an organization. Shukti, you had a question?
Yeah, so Phanish, you mentioned that the agents might not be aware that they are part of and their actions are contributing. So does that mean the identifiable boundaries is from the eyes of the researcher, or
Correct.
even if the agents? So it's up to you where you draw the boundary, right?
Exactly. So the idea of the organizational stance is that all these four properties are really in the eye of the beholder, right? Okay. None of the system components themselves might be aware of this. So this degree of abstraction may seem a bit weird, because normally we are dealing with human actors and human systems with, often these are firms or startups or teams or something. But you'll see that the general principles we're talking about would apply even if you're thinking about designing a set of drones. Okay, if you're putting together a team of drones to do some exploration of some kind, then everything I said on this page would still apply. Okay, so it is really at that super abstract level. And this has value in a couple of different ways. One is it really forces us to put on the table, why do we need to be more specific? What's the gain in being more specific? Sometimes we'll have to be, but then this is a good starting point saying, do we need that specificity? Maybe we don't. The other gain, of course, is that if you abstract it to this level, there's a lot of useful insight to be gained from studying the results in other literatures, which also have been dealing with complex systems of this kind, right? So a lot of the work in complex adaptive systems is actually very relevant for us, except the entities in their system are not human, but they are organizations by this definition. And a lot of their results and ways of thinking about problems and modeling stuff can potentially be useful for us. So that's why adopting this stance, I think, is quite generative. It opens up discussion on a number of different dimensions. So for instance, we've used this approach to study everything from small teams to platforms and ecosystems to open source communities, right? And the questions are always going to be very, very similar once you recognize it's an organization and it's a multi-agent goal-oriented system. So in this class, when we talk about org learning, this is the idea of an organization that we have in mind, right? And you can now ask yourself, is the particular phenomenon you're interested in, where is the organization in that phenomenon? Is it one of the actors? Is it a set of organizations you're looking at? Is it an ecosystem of them? That's a question that you will have to answer for yourself. Okay.
Hello, Phanish. Thank you for your explanation. And I was just hoping to ask, the definition we use here, how broadly can we say this when we were talking with others? So in your book, like chapter 1, there was a lot of definitions about organizations. And I think your definition here really makes sense and really is clear for doing research. And was wondering how I can, may I just like assume this is what others would understand for organization?
So it depends on the audience you're talking to, Jungyu. So if you're talking to managers, I usually make this point very explicit.
Okay.
I say when I'm teaching about organization design, I'm really talking about the design of any group with a goal.
Mhm.
Okay. And once they get that point, they actually see the similarities across levels of aggregation and so on. So they understand then that everything we talk about, for instance, about division of labor, would apply in a team, would also apply within a company. If you're talking to academics, it's even easier. All you have to do is cite the book.
Ah, okay.
But to be honest, this is not our statement at all. In fact, if you recall from chapter 1, this is simply a collection of the common elements in the most widely used definitions of organization. And we list everybody who's used these definitions in a table. So you can cite any one of them. You don't have to cite only us. All right. But my sense is that this is not a controversial point anymore. I mean, already this sort of way of thinking between the first paper we wrote on this in AMR and the book has upwards of 500 citations or so. So people are getting used to thinking about organizations in this way, I think.
Thank you very much.
But if you run into reviewers who challenge it, I think what you could do is in the first instance, cite our work, or you could go back and look at the table and pick somebody who looks older and deader. Okay.
Thank you.
All right. Next, what is bounded rationality? In particular, what is bounded adaptive rationality? Because that's going to be the working hypothesis in everything we talk about in this class. So the idea here is that we assume that individuals will tend to make choices that in their belief system increase the possibility of attaining goals that are currently most important to them. Okay. It's not very complicated, though it's very wordy. It just says at any point, people do the things that will, in their view, make it likely they'll get what they want. It's pretty straightforward, okay? But it is different from the traditional assumption of rationality in a number of important ways. First, nowhere in this definition are we saying that goals are constant. So people may change what it is they want at different points. So there can be preference inconsistency over time, right? In fact, the empirical evidence is pretty solid that we don't have consistent preferences in the large class of behaviors, okay? In some we do. And this is really, again, a point that I want to return to again and again. A lot of the classical assumptions of rationality that come from microeconomics, for instance, are very good approximations in certain social situations, such as buying and selling in markets. And I think finance comes closest to approximating the conditions under which those assumptions hold. But in organizational context, often these assumptions don't make any sense, right? And it's for us to know when they do and when they don't. And ultimately, the data will tell us if we are right in discarding these assumptions or not. But my view is we have enough evidence at this point not to go in making the assumption that goals are constant. Sometimes they are, very often they're not. So this definition does not presume constancy of goals. Second, this is really crucial. We don't assume that your representation of the world is accurate. Okay. And I mean accurate in both the first and the second order sense. In the first order sense, it's not accurate in the sense literally people don't know the possible set of actions and their associated payoffs. But they also don't know them as unbiased probability representations. Okay, so we don't even have PDFs which are unbiased and accurate. If we do have PDFs which are unbiased and tell us what's going to happen, then that's just a version of assuming we already know, right? In expectation, we know. So neither we know in deterministic terms, nor do we typically know in expectation terms what the true state of the world and what the associations between our actions and outcomes are. That's the implicit idea being channeled in the definition given above. Okay. Third, it does not assume maximization. It assumes a tendency towards maximization. It says individuals tend to make choices. And you'll see in a little bit that this is also very crucial to thinking about learning, because this point on maximization connects very tightly with the notion of exploration. Okay, this is very central to learning, so I will come back and explain why this is so important. But for now, I just want you to process the point that this definition of adaptive rationality does not assume maximization. And finally, nothing in this definition says learning processes are infallible. In other words, this is not an approach which says learning means improvement in performance. Okay, very often people make this assumption that learning is equal to an improvement in performance, but it is not. So I just want to write it here so that we are not going to lose sight of this point. Nowhere in this set of 4 lectures are we ever going to make this assumption. Okay, what is learning then? So as you've probably seen from the readings you have been exposed to, it's really a change in beliefs and behavior as a consequence of experience. That change may or may not lead to an improvement in performance. Sometimes it does, sometimes it doesn't. And we often are very interested in understanding when it does and when it doesn't. Okay, but we're not going to make the assumption that learning is an infallible way towards improvement in performance. So you might then ask, how about the org learning, the learning curve literature? Don't they show this reduction in costs and an improvement over time? That's true. But what we are really going to see is that that's actually a special case. Okay, that can happen under some circumstances, but it is by no means guaranteed. And of course, the speed at which it falls is also partly going to vary across circumstances. And that is partly what we have to explain, right? If learning was infallible, everybody's learning curve would look the same and it would all hit zero costs or very close to zero very fast, right? It doesn't. So the fact that it doesn't and there's variation is exactly why we think we should not make the assumption that learning is infallible. And last but not the least, the point that the representation is not accurate is really the heart of this entire course. Why? So if you imagine agents entered their task environment with a perfect understanding of the world, there is no role for learning, right? Omniscient agents don't need to learn. So learning is an inescapable consequence of bounded rationality. It's precisely because we don't know our task environment completely that learning matters. Okay, so hidden in these very few words at the top, the definition of adaptive rationality is actually a lot, which is pushing in some sense away from the classical definition of rationality, while preserving the general idea that of course we do expect agents to try and do things that get them what they want, right? So they try to do it based on their beliefs of what they need to do to get what they want. And they may change their views of the world through learning, but none of this assumes either constancy of goals, accuracy of representation, maximization, or that learning is infallible. Okay. If you wanted to, in a bit more detail, you could think about it very explicitly like this. So there is some objective task environment out there. Okay. And there is an actor, which could be an individual or a group of people or a firm. And this actor has goals. They want to do something in this task environment. They have a representation. They have a belief system, which might be inaccurate, which tells them what the task environment might look like. And they have a system of making choices given their beliefs. Okay. This is the core. The big difference between the traditional way of looking at rationality, which is the first column, global rationality, and the second is that, unlike in the traditional approach, which assumes that goals are constant, representations are correct, at least in expectation, and given your representation that you maximize, the definition we adopt makes none of these assumptions. So utilities could be unstable. It's possible that your representations are inaccurate. In fact, if they weren't, we would have no role for learning. So the second row is really the crucial reason why we study learning. And even within your choice, your belief system, you may choose sometimes to take actions that are inconsistent with them, which is called exploration, right? Now, a very important point to bear in mind, by the way, this distinction is not mine. This is classic. This comes from Simon. And he gave these definitions, which I've summarizing here in a table. Okay, so you can see the differences between the two. What I want to point out is when we say bounded rationality, there are actually many forms of boundedness embedded within the adaptive rationality framework. Okay, many. First, there's ignorance. So your representation may not be accurate. Second, there's instability. You might be inconsistent in your preferences over time, right? Third, you might not be maximizing, but you might be satisfying. And fourth, you might actually make some errors in your choice. Given your choice, you might still not pick the first best action because through some form of exploration or some kind of noise or error, you might actually end up taking an action other than the one that looks the best in your representation. So all of these are forms of boundedness. Where it gets really interesting is that some of these forms of boundedness correct for each other. Okay, that's a beautiful and interesting point. So let me just give you one example of that and we'll come back to others later. So given that our belief structure about the world is not perfect, it actually makes sense to sometimes make errors in your choices, given your belief structure. Does that make sense? Maybe I'll give you a concrete example. Let's say that you have two possible options, A and B. Okay, and let's say the true payoff is, let's say 10 and 7. Okay, let's say your beliefs about these actions are 5 and 7. Okay, these are the true payoffs. These are your beliefs. If you were to make no errors and maximize given your beliefs, what action would you pick? You would pick B. Correct? And what feedback would you get from the world? That you were right. But by doing this, what have you just done? You're paying an opportunity cost of not discovering that there's actually another action with an even better payoff. But suppose instead of going strictly by your belief system, suppose sometimes you made mistakes. Okay. So instead of picking the action that you thought had the best payoff, you pick the other one. That's how you discover that actually you may have a better payoff hiding somewhere else. So these kind of interactions between the different forms of boundedness of rationality are also very crucial to understanding what's happening in learning. Okay. So these ideas that I'm expressing in a very simple and unscientific way here, you will see are at the heart of a lot of the models that we build. So a lot of the results in our models come from effects of this kind, where there's a compensation effect between different kinds of boundedness in the system. Okay, but our working hypothesis is going to be this column on the right, which is this idea of adaptive rationality. Any questions on this? Are we okay? All good? Okay. Third, so what's learning by doing? It has other names in the literature. So it's useful for you to know that even though they use these different terms, they're really talking about the same thing. So learning from experience, decisions from experience are sometimes synonymous. There's, confusingly in our field, a branch of research called experiential learning, which you might think is the same as learning from experience, but it's not. So one of the things I've discovered the hard way is if one of those reviewers get their hands on your paper, you're in trouble. Okay, so there is a class of work on experiential learning, which is really more about the fact that people share and learn together in classrooms, for example, or even in shop floors or in teams. And that's a very valid and completely useful set of ideas, but not what we're talking about here. So when we talk about learning by doing, we're talking about taking actions based on your beliefs, on your representations, receiving some feedback from the task environment, changing your beliefs, and eventually the behavior. And this entire sequence is captured in the picture I've drawn on the right, which is a learning cycle. So this picture is going to lie at the heart of a lot of the modeling work we do. And if you have done the preparation exercises, you can already probably see how the code that you wrote and worked with is actually capturing exactly this cycle. Right? So if you look at the iterations we do in the do loops in our models, this is what's happening. So agents start with some beliefs, some priors, some representation. They take actions based on those. They get feedback. And based on that outcome, the feedback, which comes from reality, right? The feedback is the only contact in some sense with reality. Everything else is in the mind of the agent. And then they are changing their beliefs. They're updating them through some kind of learning process. So learning is really here. I can't write here. Okay. The part that is learning is between the outcomes here and the beliefs. This is really the heart of where learning is occurring. Okay, that's where the action is. So how do you convert your feedback signal from the world into a change in your beliefs? That's at the core of the learning process. So this is called a learning cycle. Okay. Now, another aspect of learning by doing, which is quite important, is firstly, this is different from social or vicarious learning. So learning by doing is learning that agents are engaging in by their own interaction with the task environment and getting some feedback and then updating their beliefs. So that's the learning cycle. In social learning or vicarious learning, which we'll talk about in the next session, you don't have to directly interact with the task environment yourself. You might be able to get the beliefs of other actors through conversation, through communication, through social influence, through diffusion, through a variety of mechanisms. But the key difference between the two is in learning by doing, you get your feedback signal directly from the task environment through your own action. In vicarious learning, you don't. You get it from the indirect learning of other actors. Okay, so that's the core difference. So today we are just going to be talking about learning by doing. Next time we'll expand this to talk about social and vicarious learning. There are two other properties which are very important to bear in mind. I've said this implicitly, but I just want to make it very explicit. The value of actions are only discovered through action. Right? So you can only learn the value of something by trying it. That's why this is also sometimes called trial and error learning. Okay, I don't get feedback on actions I don't take. Very crucial point, right? So learning by doing implies that you can only learn by doing, as the title says, right? You cannot learn by not doing. And maybe a business context where this difference is really stark and is absolutely crucial is think about the difference between corporate headquarters in a multi-business company making resource allocation decisions. Should I put this much capex in business A, this much capex in business B? And compare that to a mutual fund manager making investments in the capital market. Okay. In the case of the corporate headquarters, the only way they can know the value of investing in projects in division A versus division B is by actually investing in them. But in the mutual fund manager's case, if I don't buy stock in Apple, I still get a signal of the performance of Apple because others are buying stock in it, right? Very crucial difference. So learning in markets is quite different from learning within the organization because this counterfactual of what would have been the outcome if I had chosen it is typically not available within the organization. It is more likely to be available in market-like settings where many people are also taking the same action. Okay, so very crucial difference. So this is really also referred to with other technical terms we'll recognize when we come to them later. But for now, I think the point to bear in mind is learning by doing requires doing. Okay, you cannot learn without doing. Hence, it's called learning by doing. And last but not the least, in typical learning by doing actions, there is usually a strong incentive to earn, not just to learn. By which I mean, we are not just engaging in experimentation to figure out like what the world is. That's called search. We'll talk about that in some depth as well. But in every period, I care also about the actual payoff I receive. Right? So we are sampling to earn, not only sampling to learn. We're doing both really. Okay. There can be situations where you purely sample just to learn, where we really don't care about the payoff we're getting in every period. We just care about trying out different things and gathering all the information. But in many circumstances, as you can imagine, this is not possible. When the cost of this kind of experimentation is prohibitive, then you typically have to sample to earn and not only to learn. Okay. These are really the core properties, if you like, of learning by doing. So actors taking actions based on their beliefs, receiving feedback from the task environment, changing their beliefs, that's the learning cycle in the picture. This is captured in this picture, and it's different from social or vicarious learning because there's no other actor necessarily involved. And the two key properties here are you don't discover the value of actions without taking those actions. And you have an incentive not just to learn about the environment, but also earn while you're learning. Okay. And if you want one simple example, which we can use as a running example, is think about capital budgeting, resource allocation in a company across divisions. Think about hiring different types of employees or different types of faculty. Right? So I can think about, should I hire from Wharton? Should I hire from Michigan? Should I hire from Stanford? All right. I don't know until I try it. The counterfactual is very hard for me to see. Okay. But of course, if I'm hiring for the core to teach the MBA core, there is a counterfactual. I just need to look at my peer schools who are also hiring for the core. And then it becomes more like the mutual fund manager. So the more idiosyncratic my investment, the more it looks like learning by doing, where you have to take the action to realize the value. If what you're doing is generic, many other people are trying it, then you can get feedback without actually having to take that action. That's really the core difference between the two. Okay?
May I ask a question?
Sure.
Yeah, I think this is a great point. And I was wondering, is there, how do people explain the change of beliefs, because people learn by doing, learning by doing, it feels like if I know that I was wrong at some point, and so I learned, then it kind of feels like I can think of like my other assumptions could be also wrong. Are there like some explanations or theory for this?
Yes. So the core of it is that human learning is driven by prediction error. Okay, and that is the same assumption in all the models that I'm going to show you as well. And this is very well founded psychologically. It in fact occurs at subconscious levels. So there's a lot of evidence showing that even the way our mind works, like some massive neural net, is driven by the feedback of prediction error. So given our belief and given what happens, the delta between the two becomes the signal through which belief updating takes place. But of course, how much we update and how little we update and how many other things we update at the same time This can vary a lot. Okay. But what does not vary is that all learning is really assumed to be driven by prediction error, the gap between what I thought and what actually happened. So that's really the common assumption. Okay. Later in the course, you're going to read, I'll just get to you in 1 second. Later in the course, we're also going to read a paper by Linda Argotti and Sankili and others in management science. And they gave a very useful summary of this literature, which I would like you to be familiar with. Not today, but later. But what I want to point out is that they explain this learning cycle in the case of organization learning by adding some details about the processes that are under the hood when you look at the organization as a bunch of actors rather than a single actor, right? So it is always the same cycle of beliefs, actions, outcomes. But in addition, you can think about the stages between the arrows and parse them more finely. So you can think about knowledge creation. That's the act of converting your outcome into a belief. You can think about knowledge retention, which is about memory. So where do you store this, right? In the case of a single actor, everything is happening here. But if it's a group of people, then we have to think about, is there like a database of some kind? Is there some document somewhere where we store this? There's a question of transfer. So if the organization has to learn, somehow what you learn must be accessible to me. And what I learn must be accessible to you, right? Not just codified, but shareable. So transfer becomes important. And finally, search, which is the process of going from your beliefs to the actions, right? Do I stick with the actions I already know, or should I try some different kinds of actions? That's the idea of search. So the learning cycle is fundamental, and that's the movement from beliefs to actions to outcomes. But if you start looking at the organizational processes in which this learning cycle is embedded, then we might move things up a little bit more towards the macro end of the spectrum and start looking at processes like knowledge creation, knowledge retention, knowledge transfer, and search. That's what they do in their paper. But the reason I draw it this way is to make the point that these are fully compatible, right? There's no inconsistency between these two ways of looking at it. It's really a question of how fine-grained is the resolution of your microscope, right? So if you really drill down to the max 10x magnification, what I'm saying is at the bottom, the atomic structure of this is really the learning cycle, right? Going from beliefs to actions to outcomes again and again and again. Anjul? You're on mute.
Yeah. I was wondering, so when Cyrus and March talk about the formation of aspiration level, they talk about historical and social, right? Are these two different stages when we talk about learning by doing and vicarious learning and the formation of aspiration level? I was just wondering.
Yes, that's correct. So firstly, in this picture, in this learning cycle, you may ask, where is aspiration level, right? It is implicitly there because essentially what happens is when you get an outcome, I said all learning is driven by prediction error, right? So what's the prediction error? The prediction error is the difference between your outcome and your expectation. And your expectation in some cases could just be exactly your aspiration. In many models that we use, in fact, the two are treated as identical. Your expectation is your aspiration. So the difference between that and what you get is your prediction error, and that then drives learning. But this is all in the case of a single actor. Now imagine we had a group of people doing this. Then in fact, we can make our aspiration based not just on my past performance, but on the performance of others in the system. And now that gets us into the world of social learning or vicarious learning, right? But today we're going to focus just on the case of one single actor alone in this world, and their aspirations come from their own past performance, and they update that based on prediction error. Next time, we'll see how to extend it when we start thinking about other actors in the system and their performance as well. Okay, but the short answer to your question, to summarize it, is social aspirations is really a form of vicarious learning. Okay. Any other questions? All right, a related term here, which is online versus offline learning. So what's online learning? It's really the same as learning by doing, or learning from experience, or trial and error learning. It's just another term for it. Okay. So if you hear this jargon sometimes, and the reason I'm giving you this jargon debrief is because, as I said, we are playing at the intersection of three quite different literatures, four really, if you count computer science. So we need to have in our head like a dictionary of terms that mean really the same things, even though people call them different things. So online learning is really learning by doing. It's experience that arises from direct interaction with the environment. You pay a cost for it because you take an action and you get feedback, right? That's online learning. In offline learning, in contrast, there's no direct interaction with the environment. Okay, so it could come from things like vicarious learning, by learning from others. It could come from knowledge transfer, where others simply teach you what to do. It could also come from prototyping or simulation. Right? That's an interesting variant of the idea of offline learning. So I don't need to have somebody else, but suppose I build a good enough model of the world. I can run my experiments and learning within the model and use that to improve my belief system. Of course, that's only going to work if my simulation is good. Right? If I have a good simulation, this can work, otherwise it won't. But you'll see that building prototypes, for example, right? Or building a CAD model, or in our world, building a simulation model, say of network diffusion. These are ways in which we can actually do some offline learning. And the crucial point really is I'm not actually taking an action in the real task environment. And therefore, the signal I'm getting is also not from the task environment. So the simplest way to distinguish the left and right column is if your signal from which you learn comes from the task environment directly, it's online. If it's not, it's offline. Okay. All right, let's switch gears and talk a little bit about how our friends in computer science talk about these problems, because they've been dealing with learning for a long time. And of course, now this has become super crucial because this is at the heart of modern machine learning and AI. Right. So it turns out that many of the problems we've been working in our field, these guys have also been working in slightly different flavor and very different technologies of how they go about solving these problems. Some are actually the same, but some are very different. And to understand their world and their language and how they think about it, you have to think about a concept called a decision process. Okay, so what's a decision process? It has the following elements. First, there are states. So states are, you can think of them as conditions of the world. Okay, so it's raining today or it's not raining today is a state. Okay, you're an honest person, you're not an honest person, this could be a state. The sun is shining, sun is not shining, that's a state. Within every state, there is a set of actions, and associated with each action in each state is a reward. All right. So the two key elements I've said so far is there are different states of the world, and in every state, there are certain possible actions, and associated with each action, there's a possible reward. But the crucial point here is that the reward associated with an action is contingent on the state. So the same action, if I took when it was raining versus when it was not raining, might lead to different payoffs, where the action in question is carrying an umbrella. So if I'm carrying an umbrella when the state is it's raining, that's great, positive payoff. If I'm carrying an umbrella around when it's not raining, then I just look like a pseudo-intellectual. Okay, very bad payoff. So it's the same action, but the state is different and therefore the payoffs are different. So what's learning in this world of decision processes? So learning in their world is actually the discovery of the state and action contingent rewards, the R function, the RSA function. Okay, because once you learn the associated rewards for every action contingent on every state, then it's just a question of picking the best one. That's the optimization problem they're typically trying to solve. Okay, and you can't do this in one shot. That's why you need learning, because you don't begin by knowing this. You have to learn this through some process over time. And here are the different ways in which they optimize this problem. Actually, let me come to that in a second. Let me also point out another jargon term, which can be quite confusing because it's very similar to other terms, but means something quite different. In the world of computer science, they often refer to reinforcement learning tasks or an RL task. And it's a particular form of the decision process in which the knowledge of this reward function, RSA, can only arise from the learning agent having taken the action A under state S. Does that sound familiar? This is exactly the same point about the corporate headquarters making an investment and learning the value of a project versus a mutual fund manager who can learn the value without having to invest, right? So this in their language is called own action dependence, or sometimes endogenous sampling. Okay, but they really mean the same point, that you can't learn the value of an action without taking the action. And they also recognize very clearly the difference between this and vicarious learning, which is learning from the actions of others. And they also have an interesting alternative, which is also quite popular in behavioral game theory, called regret-based learning. What is regret-based learning? Regret-based learning arises when you get a signal not just on the action you took, but the action you did not take. Right? So a mutual fund manager can engage in regret-based learning. Shit, I should have invested in Apple. Okay, that's regret-based learning. But the corporate headquarters does not have this luxury. They're engaging in a reinforcement learning task. because they only get the feedback on the actions that they actually have taken. Okay, that's the key difference. So we can think about different categories of reinforcement learning tasks. This is from the book by Sutton and Bartow, which Sang-Yoon very nicely summarized in a project we had together. So I've just borrowed from that. The jargon can be helpful, and I'll try and explain the jargon a little bit. So if you encounter it, it won't sound like Greek. Think about a world in which there's only one state. Okay, there's this one state and there are different actions. And now based on those actions, you can choose which action is the best one. This in the world of decision processes is called a non-associative task. Okay, it's a non-associative task, just one state. And our goal is to try and find the optimal action. Okay, this is typically the kind of model that we'll be working with in this class. So this is captured in the multi-armed bandit problem, which now I guess you are somewhat familiar with, right, based on the pre-work. So this is a classic example. So it's a single state because the payoffs to the arms don't change over time, right? In expectation, they remain constant. So there's just a single state of the world, and your task is to try and figure out which arm should I pull to get the best possible payoff. That's the simplest kind of decision process. And very often we don't do more than this. Okay, and this is already complicated. Then there are associative tasks in which there can be more than one state. Okay. And within that, if there are more than one state, we want to distinguish whether the state depends on the previous action or it does not. So if it does not, then it's called an associative task. If it does, it's called a full reinforcement learning task. All right. And here, obviously, it gets a lot harder to find what's the optimal set of actions because it's not just one, right? It has to be across all states. So you've got to find the set of optimal action per state. And that's called an optimal policy. And figuring that out can be very difficult. So let me illustrate the difference between these three by using a very simple idea from game theory. So here's a game that we're all familiar with, right? The Prisoner's Dilemma. So think of this from the perspective of player one. Okay, let's say you're player one. And let's imagine that player two always picks confess. Okay, so player two never changes what they do. So player two's actions are fixed. It's just a column. It's the first column. And let's imagine that player one actually begins by not knowing the payoffs associated with confessing and not confessing. So they got to learn this by trying it, right? Learning by doing. This is a classic non-associative task. Okay, it's a non-associative task because essentially the world is constant for me. The other player is standing still. And given the stationary nature of the other player, I just have to figure out which action to take. That's a simple multi-armed bandit problem with just two arms. Confess, not confess. I can try both, look at the feedback and learn which is better. That's a non-associative task. Okay. Now, what happens if it's an associative task? So imagine that player two randomizes between confess and do not confess. All right. So in every period, they're basically flipping a coin and deciding sometimes to confess, sometimes to not confess. So the states are changing, but not in any way connected to your own actions. They're just doing some stuff, right? We don't know why they're doing it. So now we're dealing with an associative task. Okay. And finally, this is the most complicated case. If both players start out not knowing the payoffs in this picture, they have to learn them by trial and error, and each is responding to the outcome in the last period. Then we have a full reinforcement learning task. Why? Because the states are changing. So my payoff to action confess depends on your action, which will change the state for me, right? So if you take as player two the first column, my payoffs as player one could be either -8 or -10. But if you take the second column, then my payoffs could be 0 or -1. So the states are changing, and the states are changing in response to my past actions. Right? Because if I picked confess and you picked confess and we both got -8, you might want to change your action in the next period. So that's the most complicated case. So even this very simple game with two players, two actions is actually an instance of a full reinforcement learning task, right? Where the states are changing and they are changing contingent on actions. So that's the space, if you like, of reinforcement learning tasks that people in CS very often will categorize their problems in this way. So how do they solve them? Because they're interested really in one thing in the end, which is whichever task we have, how do I find an optimal policy? Okay. So to give you an example of a full reinforcement learning task, which is exercising a lot of interest from computer scientists around the world, is the case of the self-driving car. So self-driving car is dealing with a full reinforcement learning task. It has to learn how to act in different states, but the state it finds itself in is itself a function of its past actions. Because it's playing a game with other cars, right, on the road. So it's really like a game between cars. So that's really the most complicated problem that they can imagine. The case where the world is constant and you just have to figure out which action to pick is the simplest. That's the one we often are modeling, right? But the reality is that the world doesn't come that simple. We choose to make simplifying assumptions, and we try to capture that simplicity in some formal way to be more rigorous about it. But it's good to be aware that behind the scenes, there are this entire set of possible scenarios. And for each of these, we want to be very clear in our head what's going on. Are the states constant? Are the states changing? If they're changing, are they changing independent of my action or conditional on my action? Okay, and being aware of that will give you an easy way to understand what's in the literature in computer science that you might be able to reach out to and learn something from. Okay, that's the reason why I'm showing you this jargon, to map it back to the jargon that we are more comfortable and familiar with. Shruti?
So is associative learning like learning in one context and then extend?
No. So unfortunately, this field has so many similar sounding words which mean completely different things. Okay, so associative in this case is a homonym. This is a non-associative task or an associative task. Associative learning is something quite different.
Okay.
Okay. So it's always helpful when you come across these terms to ask, is this a description of the task environment or is it a description of the learning problem? That's the way I get my head around these things. Otherwise, it's very easy to be confused because people are using almost identical terms for very different things.
Thank you.
Okay. Which, by the way, we have a paper showing that that's much harder to deal with in the case of synonyms. Right? We have a proof showing that homonyms are much harder to unlearn than synonyms. So synonyms are easy. If you use a different word for the same thing as me, we can converge in our communication. But if we both use the same word to mean completely different things, then the unlearning problem is very hard. So a recent paper that just came out in management science. Okay. So how do computer scientists actually solve these reinforcement learning tasks? So broadly speaking, they have three strategies. The first is dynamic programming, right? You might have gained some exposure to this. I don't know, in any of the core classes, maybe some of you have, some have not. But what it requires is a full model of the task environment. So if I understand the task environment in the sense I can represent it mathematically, then I can formulate the decision process in a formal way, which is called a Markov decision process. So this has the Markov property, which means that the state at time t+1 is fully determined by action at time t. So if I know the action at time t, I know everything I need to know about the state at time t+1. Okay. Given enough information, almost any problem can be treated as if it's a Markov decision process. So you'll sometimes see the jargon of MDP. That's what they're referring to. So an MDP or a Markov decision process is a formulation of the reinforcement learning task with the assumption that the states at time t+1 are fully determined by actions at time t. Okay. And then, of course, you can use the mathematics of dynamic programming to optimize this and find the optimal policy. It's quite complicated, hairy mathematics. But from our purpose, not only is this typically not very relevant for two reasons. One is the typical problem we are dealing with is one that we can't characterize completely using mathematical equations. We don't know, right? And we certainly don't expect the agents to know. So this approach to trying to formulate the entire problem as a fully specifiable mathematical model and optimizing it is quite limited, I think, for the kind of problems we're dealing with. There's a more sophisticated and important reason as well, which is often we are interested not in optimizing anything, but in describing stuff, right? We're doing science, not engineering. So if you're doing science, we want to understand what produces the data we see in the world, not what's the optimal way to solve a particular problem. That's engineering. So dynamic programming is an engineering approach. It tries to find the optimal solution for a problem. The behavioral approach, which is what science is about, is to say, given we observe this data in the world, how can we explain it? And it's highly unlikely we can explain it by assuming people are doing dynamic programming, right? They're typically not. So this is one method, which is very standard in CS, but of fairly relevant, limited relevance for us. A second method is called the Monte Carlo method. It's really just a way of sampling. Okay? It requires a period of very extensive sampling in the task environment without much by way of consequences. So this is an offline process. Okay? An example of this would be if you're training your algorithm to play Go or play chess. That's a full reinforcement learning task, right? There are multiple states because each state is what the other person did. For given what they did, you have a set of actions. And obviously your payoffs to your actions depend on the state, but the state itself depends on your prior action. So it's a full reinforcement learning task, right? The way we can often train these is to play millions of simulated games so that you can check out all the possible branches of the actions and learn from them and build a representation of what happens each time something is likely to happen in the branch of possibilities. So it's an offline process and it requires extensive computation. And more importantly, it requires that you be able to get some feedback about what's going to happen without it actually happening, right? You can play a game that makes it easy. So you can't train a car this way, right? There is a limit to how good your self-driving car will be if you only train it in a simulator. You have to throw it in the real world at some point because the kind of things that happen in the real world are not going to get captured in the simulation unless your simulation is as good as the real world, right? That's the problem. So Monte Carlo methods can be very effective when you can build these playgrounds where you can do offline sampling of all possibilities using a simulation of some kind. And it works very well, I think, from my understanding, for building reinforcement learning algorithms to play games, but not that effective once you start introducing real world phenomena. So what do they do when they have to solve real world problems? In other words, what do self-driving cars look like? How do they solve the reinforcement learning task? And I think it's kind of a beautiful point to bear in mind that when engineers are trying to build self-driving cars, they discover that the only feasible way to solve the full reinforcement learning task is to use a technique that seems to look very similar to the way humans actually solve problems in the real world, which is called temporal differencing, or really it's prediction error based learning, right? Or it's learning by doing in our language or online. So it's a really striking point, right? So nature as natural selection as an engineer has kind of discovered the same algorithm that computer scientists have discovered as a way to solve the problem of the full reinforcement learning task, which is really telling you a couple of things. There's a good chance this is the best way there is to do it. Okay, we have no proof that there is no better way to do it, but it looks likely it is, because both natural selection, which is operating over millions of years through trial and error, and human engineers have kind of converged on the idea that if you want to build an actor or an agent that has to tackle a full reinforcement learning task, the way to go about doing it with a reasonable degree of effectiveness is to use these techniques, which they call temporal differencing, we call adaptive reinforcement learning, but it's the same thing. At the core of both of these is the idea that we use prediction errors, the difference between our prior expectation and what happens, to update our beliefs. Okay, that's it. So even the most complicated self-driving car at its heart is working in exactly this way. It's using a structure of beliefs. It's looking at expectations, getting the feedback, comparing the two, changing beliefs and acting again. So that's reinforcement learning in the context of computer science. Okay, so it's online learning really. Any questions? Let's pause and see if anything needs clarification, elaboration on. I've covered a lot, and we're going to switch gears and now start talking about modeling this stuff in our world. But any questions at this point? Akin, Sangyun, you guys want to add anything? You've been thinking about this stuff for a long time too.
For the moment, not necessarily.
Sangyun? All good? Okay. So what we've done so far is basically just set up some terminology and jargon, but hopefully some of this is already beginning to clarify some very basic differences between things like learning by doing and vicarious learning. And again, the points that I want to make sure are very solidly fixed in your minds is that when we're talking about learning by doing, we're really talking about a process of actors taking actions in a task environment, getting feedback, updating their belief as a function of the prediction error between the feedback and their belief, and then going through the whole cycle again and again, right? And crucial to that are these 2 points, that you don't get the feedback unless you take the action. And conversely, you don't get feedback on actions you did not take, right? That's learning by doing. And further, the last point, I guess, to mention is that in these scenarios, you often care about payoff in every period and not just learning about the world, right? So take it back to self-driving cars. You want to build a self-driving car that in every period is keeping the accident risk low. You can't build a self-driving car that doesn't care about the risk of accident because it's learning about how to drive. right? That'd be a disaster. So in much the same sense, if you're a human investor, right, trying to make decisions on which portfolio of things to invest in, you do care about learning which is the best investment opportunity, but you also care about profits every period, right? So sampling to earn, not only to learn. That is really, really crucial. So this bundle of attributes which come together, which is, acting in a real task environment, getting feedback, learning from that, only getting feedback on things that you have acted on, not on the things you haven't, and caring about the payoff cumulative across periods and not just learning about what the environment is. That bundle of things very often goes together in our world and is called learning by doing. Okay, so these are the elements. I've tried to break it down, but they come together really very often and are called learning by doing. Piyush?
So, as in on your previous slide, Phanish. Sorry.
Yeah.
Sorry, we are in a room right now, so I think there's a problem.
You have to turn off the audio of the room, I think.
Is there a way to turn off the room's audio? That's relatively easy to do.
If you go on the participant list and then click on Amphi 301A,
Nice.
it will give you option to mute.
Thank you.
Can you hear me now?
Yeah.
Amphi 301, right? Yeah.
Yes, I think.
Now it's
Okay. So, as in my question was on this slide, Phanish, that does it have to be that these are three independent methods? Wouldn't it be that somebody is using like temporal differencing, or as in we are learning from what you've done previously, but the underlying process is a dynamic programming process or an experiment?
Yes, no, that's very true. So in fact, I think in sophisticated reinforcement learning algorithms like self-driving cars, they will do all three. So there will be like a baseline prior, if you like, which might come from dynamic programming. There'll be some Monte Carlo type method of trying to populate your belief structure by sampling offline, but then it will never be perfect, right? So the last mile of learning in some sense will be in real time. And that you might then do through temporal differencing. And I think the same, if I recall correctly, when I read about how AlphaGo was designed, is also quite similar. So AlphaGo has a lot of learning coming from Monte Carlo simulation, but it learns in the game as well. So it's not just that it comes into the game with you and is learning stops. It's learning in real time from what you're doing as well. That's temporal differencing. So there's usually layers of this intertwined together in many solutions. It's not mutually exclusive. That's absolutely correct. Shukti?
Learning by regret, was it that you mentioned in your previous slide? Is it just another word for prediction error-based learning, or does it also include interpretation-based learning?
So regret is not about prediction error. So prediction error idea is very simple. Let's say I have an expectation, okay, and I get an actual payoff. This is my prediction error, okay? But this is for the action I took. Regret is telling me that I had an expectation for an action I did not take, right? And somehow I get a signal on the performance of that action. That's regret. So regret is telling me if I had taken that other action, then I would have gotten this payoff. That's why it's called regret. But regret is ruled out in learning by doing, because this is a class of problems where you only get feedback on the action you took, right? So if there's any doubt, always go back to the comparison of the mutual fund manager and the corporate headquarters. So the fund manager gets regret-based signals because he can see, or she can see, the payoffs to stocks they did not invest in. The corporate headquarters can only see the signal on the investments they actually made.
So this will be basically just for social or vicarious learning.
Correct.
Or,
but well, hang on. I'm not sure I should equate it so tightly. So let's take the stock example again, right? So when a fund manager gets a signal on the stocks they did not pick because somebody else picked it, that is regret-based learning. Is that social learning?
no, but vicarious learning, right?
So this is the point now where the words and how we define them begins to matter. So if you include the fact that the signal I'm getting on the other stocks comes from other people's actions, that's a social effect. So I could define this as being a kind of social learning if I like. This is the point, right? So it can get very quickly quite ambiguous. So as long as we're very clear about where is the signal coming from, is it coming from my actions or somebody else's action, we can draw a sharp line between learning by doing and everything else. Now, is that everything else, social learning, vicarious learning, regret-based learning, that might change by context and how you define terms.
So in a way, social learning might not even involve any interaction with another person.
Exactly. Social learning can be very asocial. Yeah, that's very true, right? In fact, there's a beautiful paper which I will share with you. I don't think it's in the course reading list. There's a nice paper in one of the biology journals on a summary of social learning in non-human species. So that's kind of eye-opening for us to realize, because there's a lot of social learning happening in species which I don't think are even aware that they are other members of their species around them. But it's still social learning because the signals they get are being generated by others, right? What humans uniquely do in addition to that is we also exchange beliefs. We can talk to each other, we can communicate, so we can actually exchange our beliefs about the world. But you can get a lot of social learning without any interaction at all. For example, by copying. If I just copy what others do, even though I'm not directly interacting with them, that can be helpful. I might just look at how well others are performing and use that as a competitive signal to put in more effort or less because others are doing more. I'm not interacting with them. Or it could be that the signals I'm getting are partly driven by what other people are doing. I wouldn't get it if the others weren't doing it, like the mutual fund manager. So these are all, at least in my mind, various kinds of social learning, but the exact social process and the exact kind of interaction is very different across them.
And sorry, just to follow up then, you are saying learning by doing can only happen if an agent takes an action. It can never happen if you observe and change your beliefs, for example, or like interpretation based, or
if you observe somebody else taking the action and learn from that, that is not learning by doing.
Okay.
Right? And there's a reason why we're starting with learning by doing, because I think it should be obvious. Between the two, learning by doing and social learning, the more fundamental thing is learning by doing. Why? Because all social learning depends on somebody else's learning by doing. Right? So we couldn't have got it out of thin air. So in the end, it has to always come from learning by doing. That's why it is the most fundamental building block for thinking about learning. That's why we start there. Pulkit?
Yeah, thank you.
Professor, what is the exact definition of interaction? Someone learning from someone else, is it not some kind of interaction just by looking at someone? So what is
that's a form of interaction. Sure.
So even social learning cannot be asocial, right? Then even just looking at someone.
Oh, it depends on what you mean by social, right? For most sociologists, social really means mutual awareness at a minimum.
Okay.
At a minimum, right? But you don't need mutual awareness for learning from others.
Yeah.
It can happen when others take actions that change your task environment and change the signal you get. Okay, so that's why these words and how we define them start becoming sources of major confusion. What I'm trying to give you is like the underlying conceptual structure. And then depending on the literature that you parachute yourself in, you will have to read up the local norms on how people are using these terms and then adhere to that. Right? Otherwise, it will be like my experience of sending my paper to the experiential learning reviewers. It will not go well. So that's a problem you have to figure out for yourself. I'm going to focus on concepts. You guys deal with the literature and the references and the reviewers. Deal?
Yeah.
Okay. Yeah. Jangyo.
Yeah, I was hoping to ask a question regarding the initial belief, how the initial beliefs are formulated. In your previous prerequisite videos, the initial beliefs was kind of like randomly distributed, and initial belief cannot be learned by doing because they don't have any experience yet. So yeah, so how is it
very good question. So there are at least two ways in which one can think about this. One can just assume, as often is the case in models of learning in animals, that initial beliefs are hardwired. Okay, so they may just come into the world with certain belief structures hardwired into them. So we know, for instance, even among humans, there are hardwired beliefs about avoidance of heights, of snakes, of fire. Where did these come from? We didn't get this from any social learning, right? Yeah, but much more typically in our world, initial beliefs come from social learning.
Yeah.
So vicarious learning is really a very powerful mechanism for producing those initial beliefs. Okay. But we still talk about them as two different engines of learning. But you're absolutely right that you can't even begin learning by doing without priors. And priors must come from somewhere. They don't come from thin air. And very often they come from social learning.
Okay. Thank you very much.
Okay. Any other questions? Okay. Actually, why don't we take like a 5-minute break? I need to fix something on this machine. So let's take a 5-minute break and then we will dive into modeling these things. Okay. Thanks.